Hello guys, today in this video I'll be showing you the various types of graphs and how to implement them in Python. So before that I just want to give you a brief overview on the various types of graphs. Namely, there are four types of graphs: undirected graph, directed graph, and non-weighted graph and weighted graph. So we'll come to them one by one. Firstly, let me show you the directed graph. So here there's this directed graph. A directed graph basically means that if there's a connection from node A to node B, then that doesn't mean that there is a connection from node B to node A. Okay, but for an undirected graph, if there is a connection from node A to node B, then it also means there is a connection from node B to node A. Cool. Now, what does a non-weighted and a weighted graph mean? The one that I just showed you here is a non-weighted graph. So here the path or the connection from one node to another node does not have any kind of a value, okay, or does not have any property. See, from node 4 to node 2, this is just a path. From 3 to 1, this is just a path. From 2 to 4, this is just a path, nothing else, okay. But for this graph, this weighted graph, here for node 4 to node 2 there is a value of 8, and from node 3 to node 1 there is a value of 2. So this means that various paths have various values or various properties which can be used in various type of questions, okay. And there are also trees such as binary trees and various other types of graphs which we will cover in a later video, but today I just want to show you how you can implement them in Python, okay, because I think that there are a lot of videos which show how to implement graph. They teach you the basics, they teach you many other things, but they don't show you the implementation, or even if they show you, they just write the code and not explain it properly, and not in a way that you can do it by your own from scratch. So today we'll be doing that. And now the question comes that, see, these are graphs, these are pictorial form. How can we represent them in a computer? A computer does not understand this, so we need to teach the computer, okay. So mainly there are two common ways of representing them. Those are either by using AdjacencyMatrix or by using AdjacencyList. So as you might have noticed by now, this AdjacencyMatrix, basically for every I and j index it will have some kind of a value. For a of ij, if this matrix was called A, then for a of I comma j there will be a value, either 1 or 0, in case it's a non-weighted graph, okay. 0 represents that there isn't any kind of connection, and 1 represents that there is a connection. But if it would have been a weighted graph, then instead of 1 we would have kept a value. So from here, from this node 2 to node 4 there is a connection. You can see from node 2 to node 4 there is a connection, this one. But if this was there from node 2 to node 4, this was 3, then instead of 1 this would have been 3, okay. And similarly for list, this is also for non-weighted. See, we have a connection from 1 to 2, then 3 to 1. So we have a connection from 1 to 2, then 3 to 1, then 3 also has a connection to 4, 3 also has a connection to 4, then 4 has a connection to 2. See, 4 has a connection to 2, and 4 has a connection to 2, then 2 has a connection to 4, 2 has a connection to 4. So this is the basics, okay. Now let's see how are the inputs given to us. Generally in all type of coding questions or in competitive programming, to be general, here the inputs are like this. Like they will give you a line. It might differ in various competitions in slight ways, but mostly things are like this, that they give you space separated integers. Sometimes it can be even characters, like from node A to node B. I'll show that in another video of how to do that. It is very simple actually. You just need to know the ASCII values and convert them accordingly. It's very simple, just like this. you just need to convert it. So you see, this is the 4 and 5. The 4 means the number of nodes, 5 means the number of edges, then 1 and 2, this means there is a connection. Okay, then 2 and 4, this means there is a connection from node 2 to node 4, and this is for a directed graph. So this means from node 2 there is outgoing a connection, and to node 4 it's inside. Okay, from 3 to 1, from 3 to 4, from 4 to 2. And for weighted graph, you are also given a space separated integer mode, which just represents the value of the path. Okay, like 3, 4, 5. So this means from node 3 to node 4 there is a path, and the value of the path is 5. You can see it, from node 3 to node 4 there is a path, and the value of the path is 5. Okay, so now that this is done, let's move to the coding part. See, I have also kept here the input formats. Now let's start. Firstly, I will be showing you how to do the graph using AdjacencyMatrix. So we will make our own class. I'll name this class graph AM because AdjacencyMatrix, and then we'll define various functions in it. Firstly, we'll define the init function, which is kind of the main function, and that function will get input of nodes. Okay, like the number of nodes, and then we will also get various parameters like is directed, comma, is weighted. Well, right at this point I want to tell that it is completely up to you. If the question is given to you and it said that is directed, it's not directed, or it's not weighted, then you can just do it on your own. Okay, but this one, the code that I am writing, this structure, it is a universal structure. It will work for any kind of question. You just need to write either true or false upon various combinations. Okay, so yeah, initially we will make it false. We'll make all of them false. So if we are not given any kind of value, then we will assume that the graph given to us, the data given to us, is for an undirected and non-weighted graph. So yeah, but now before that, let me just show you the way the inputs will be given. And so first let's take input. So nodes equals to int input, and then same for edges. And then let me define an object, graph equals to graph am. Will give this the value of nodes, and will give this some other value. Well, let's not add value right now. I mean, if we are given a directed graph, then we can just add a true beside this. Okay, and if we are given a weighted graph, we can add a true beside this. If we are given a weighted graph but it's undirected, we have to add a false like this, as there are multiple parameters having the same kind of value, so it might be a confusion. So but for now, let's keep it simple. So this is our object, and I'll make a list. I'll make an empty list, and for in range of edges, and this is edges because see here the number of edges are 5, so this means the number of connections. So we'll be given 5 inputs, that's why it's edges. We will be taking the input, input dot split. Yeah, so this is our input, and we will be appending this to the connection. Okay, cool. Now for every connection, here graph and edge will be passing the value connect of 0 comma connect of 1. Okay, but now we need to define the add edge. But if you have any kind of confusion, so let me just tell you what the connection will look like. The connection list, it will look like something like 1 comma 2, then comma 2 comma 4, then comma 3 comma 1, and so on. So for every connect we will get this list or this list. And now for connect of 0, this means this node, and connect of 1, this means this node. Okay, so just something to keep in mind. Now let us make our function to work. Okay, so we will be making a adjacent matrix, right? So adjacent matrix, this will be equals to, we will be initializing all of the matrix with 0. So this will be nodes plus 1, and this will be plus 1 because I'll come to that reason in a minute. In range, again nodes plus 1, no, here it will be plus 2, and yeah, and self dot is directed, this will be equals to is directed, and self dot is weighted, this will be equals to is weighted. Okay, now the reason that we are using nodes plus 1 is because we are considering our graph to start from the node 1 and not node 0. There might be some questions where the question are given there is some kind of node 0. In that case you did not make plus 1, and in that case instead of nodes plus 2 you can make it just nodes plus 1. Okay, we are doing this so that for every node, so the 1th node is aligned with the 1th index and not with the 0th. I hope this makes sense, as in matrix or in array the indexing starts from 0, that's why it is required. Okay, now let us define our add edge. So add edge, this we will pass two values x comma y, and actually let me define it more clearly. So yeah, so add edge and weighted. Okay, so we will be using this function when the graph that we are given is a weighted graph. Okay, so we will also be passing another value of z. So here what we will do is, firstly for self dot adjacent matrix of x comma y, we will make the value z. Okay, and now if not self dot is directed, this means the graph is not directed. So if this is the case, then x comma y, if it's z, then y comma x is also z. So for that we will also write self adjacent matrix of y x equals to z, and that's it. Then we will make another one just for the add edge when there is no weight. So this one will be having just x comma y, and for this we will be again doing the same thing, but instead of z we will just be giving it the value of 1. And similarly, if it's undirected graph, then we will give this matrix of y comma x is also equals to 1, So yeah, that's done. And now let's make a function to remove it. Okay, so delete edge. If we were to delete some kind of thing, then self comma x comma y, we will be deleting it. So for self dot adjacent matrix of x and y, this will be equal to 0. Okay, so just like how it was initialized. And similarly again, if not self dot is directed, then this will be self dot adjacent matrix of y comma x, this will also be 0. And that's it. I think we are good to go. But well, let me return the matrix too. So I'll define a function as return graph, and this will be having self, that's it, and this will just return the adjacent matrix to us. So this is going to return the adjacent matrix. Okay, so yeah, and yeah, oops, my bad. Yeah, so firstly we'll be testing out this input 4 5 1 2 2 4 3 1 3 4 4 2. So this is a directed graph, so this will be true, but this is a non-weighted graph, so we won't be giving, so let's just put false. Okay, and we'll be passing these values. I think these are good, and we will get our value grp as graph dot return graph, and we'll be printing for I in range from 1, and it's 1 because, as I told you before, this index 0 will be useless for us because we are starting our node from 1, that's why. So the first row and the first column will be consisting of 0 and won't be of any use. And so for any kind of operation like deleting or any other thing, searching, BFS, DFS, we will be starting from 1 only. Okay, so 1 to nodes plus 1, and then for j in range of 1 to nodes plus 1, we will be printing out grp, oops, my bad, grp of I and j, and let me separate them by a space, and then we will be printing a new line, and yeah, that's it. So before running it, let me just get the values. Oops, there's some kind of, I did a colon here, sorry. And see, we got our matrix 0 1 0 0. This one, it shows the connection between the first row and the second column. So as you can see over here, the first row and second column, they have a connection, and then here this one, it shows a connection for the third row and the second column. So this shows a connection between node 3 and node 2. So yeah, and node 3 and node 1, sorry. And then this one, it shows a connection from node 4 to node 2, and this one also shows a connection from node 4 to node 2. So yeah, that thing works good. Now if this was true, okay, so if the graph that we are given was a weighted graph, all we need to do is just add another parameter, connect of 2, and instead of add edge, we will be giving it to the add edge weighted. Okay, now let's just see this. So see, we have our values. From 4 to 2 it's 8, from 3 to 1 it's 2, then from 3 to 4 it's 5, just like this, where it is just like this. From 3 to 4 it's 5, and from 3 to 1 it's 2, just like this. So this thing works, it's fine. So yeah, that works. Now let me delete something. So graph dot delete edge. Let's delete the edge between what, let's delete the edge between 4 comma 2. Okay, so we will be deleting the edge between 4 comma 2, and then once again we'll be printing this graph, the same thing once again. So I'll just copy paste it, and now okay, I need to get the input once again since I changed my copy thing. So yeah, see, firstly, it's a little bit difficult. Okay, let me add something more. Print after deletion. Okay, I hope now it's fine. So 0 1, see, this was the connection between 4 and 2, and see, now this is 0. Okay, so that was that. So this thing works very good. Now let's move to adjacent list. Okay, so now we'll make another class. Before that, I'll just add a few spaces, and we will be requiring this input too. So let me just comment this out. So I'll comment it, and I'll copy the inputs. Yeah, now let's make a new class. So I'll call this class graph AL, which means adjacent list, and this will be having similar functions like init, self, comma, nodes, comma, is directed, comma, is weighted, and all of them will be equal to false at first. Now this is the part where our function, our graph will differ from the previous one. Okay, so as you can see over here, this was a matrix, but here this won't be a matrix. Let me just copy a few commands like this self. These are the things that we will need. So I follow DRY, don't repeat yourself. Now self dot adjacent list. Now this is going to be a dictionary, okay, a Python dictionary. And now see, we will be given the number of nodes, so we need to extract all the nodes. Okay, in the matrix we initialized all of them with 0, but here we will be initializing all of the dictionary keys with an empty list. So self dot let me first get all the nodes. So self dot nodes equals to x for x in range of 1 comma nodes plus 1. Oops, nodes plus 1. Okay, so these nodes, this is a list that consists of all the nodes. If the value that we give is the number of nodes is 4, then this will consist of 1 comma 2 comma 3 comma 4. Now for every node in self.nodes, we will be given to this dictionary self.AdjacencyList of the key node and empty list. Okay, so at this point let me just show you how the dictionary will look. This will look something like 1 like this, then 2 like this, then 3 like this, and so on. So yeah, this will be our list, and as we give values it will be appended to this. Okay, now we will again make functions for add edge weighted. If it's a weighted thing, then self comma x comma y, and now we will add to this dictionary. Okay, so self dot adjacent list of the key x, since it's weighted, so we will be also given the weight for x dot append and we will append in a list, in form of a list, y comma z. Okay, so y comma z. So essentially what this will make the function look like is, let me show you. See, 3 1 2, right? So this will make, for 3 the key look like 3, there will be a list. There was firstly an empty list, and then now it will be 1 comma 2. Okay, now once again when it will be done, see here, for 3 4 and 5 is also done once. So this time this will be 4 comma 5. Okay, for 3 this will be the list. Okay, makes sense. Now if not self dot is directed, in that case we will be doing this thing once again, dot adjacent list of, this time we will be doing it for y dot append, just in like a list, x comma z. Okay, so this is done. Now if we are given a non-weighted graph, in that case it's pretty simple. Self dot adjacent list for x dot append, and we'll just append y. So here it will be something like, for 3, since there won't be any value like 2, so let me just show you. For 3 it's 1, for 3 it's 4, so it will look like, for 3 1 comma 4. This just shows that there is a connection from node 3 to node 1 and from node 3 to node 4, whereas this one shows there is a connection from node 3 to node 1 and the cost of the connection is 2, and from node 3 to node 4 there is a connection and the cost is 5. Okay, so that's that. Once again we will check if it's a non-directed graph, then self dot is directed. If it's not, then we will do this once again. So for y we will append x, right? Okay, so this is done. And then we will make another function for deleting the edge. So for delete edge, self comma x comma y, for self dot, we will first need to, okay. Now see, the thing is, since this is a dictionary, so we need to get various things, we need to take care of certain things. For example, this won't be delete edge, this needs to be delete edge weighted. So basically, if this is a weighted graph, then you need to enter this function and not delete edge. You don't need to pass the weight, but this is just a different function. Okay, so here we will first get the list of the values. Okay, so the list, so basically we will be first getting this list. Okay, so this list, this will be equal to self dot adjacent list of x. Okay, so right now we are having a list, and then in that list we will be iterating. So for k in, k is just a variable, for k in li, the list, k will be having this value, this list. Okay, 1, 2, then k will be also having 4, 5 and more if there are more values. So if k of 0, which means the first element, if that is equals to y, then we will delete it. Okay, so from list dot remove k. Okay, make sense? Actually, well, let me just do something. No, we should not remove it from li, we should actually remove it from self dot adjacent list, and then from adjacent list from x, and from here we should remove, because li, if we remove it from li, it would remove it from that variable and not from our adjacent list, right? So this is that, and once again we will check if not self dot is directed, then we will repeat the process, and this time the li would be self dot adjacent list of y. Okay, so this will be of y, and now for k in li, if k of 0, if this equals x, then from self dot adjacent list of y, we will remove k. Okay, we will remove the entire list. So let's say if we give 3, 4 as the value to this delete edge weighted, then it will search. Firstly it will get this, it will search if the first element is equal to 4, it's not, so it will move, it will get to this list, and then it will search if the first element is equal to 4, which it is, then it will delete the entire list. And as you might have guessed that if instead of this was just 1 and I would have passed 1, then it would essentially empty our list. So it would just become like the list when it was initialized, that is, it is having no connection. Okay, so that's that. Now let's make a function when it is not weighted. So now it's pretty simple. All we need to do is from self dot adjacent list of x, we will just remove y. Okay, we just need to remove y. Since this is just a list, so we will just need to remove y. So we will be having this list, and let's say the value given is 4, so we will just remove 4. That's it, nothing else. And once again, if not self dot is directed, then we will remove it from there also. Self dot adjacent list of y dot append x. Okay, so this is done, and finally let's return our graph. So we will just return this self.AdjacencyList. We will just return this, and yeah, that's it. Our graph is done. Now let me just copy the input, as it would be the same for both the graphs. Yeah, so instead of AM, this will be just AL, and that's it. All things look good, is directed, this is true and this is true. So yeah, let's see what happens if we print our graph. Let me get the value. This was the value, right? So if I run this, see the value that I get. Let me explain it to you. See, from 1 there's a node, from node 1 there's a connection to node 2, and the value of the connection is 1. So this is a nested list, okay? From 2 there's a connection to node 4 and the value is 3, and from 3 there's a connection to node 1 and also to node 4, and the value for 1 is 2 and the value for 4 is 5, and so on, okay? And now, so this was for weighted, and if this would have been just edge, then we would need to delete this and we would copy this value and we would just run it. See, we have got our desired value. See, from 3 there's to 1 and 4, just like here from 3 there's to 1 and 4. The only thing is there's an additional property of some value or weight, but here there is not. Now let me show you by deleting something. Let's print after deletion. After deletion. So here I will be deleting something. So let's say I want to delete graph.delete edge. I want to delete something between 3 and 4, okay? And now once again I want to print my graph. So grp, and I will, okay, so I just need to change the copy one. This is the value, and I will just put it there, and see, after deletion there is no connection from 3 to 4, okay? Now let me show this to you for added range of weighted. So this will be connect of 2, this is this. Oops, we ran into some kind of error. Okay, I understood. The thing is that, as I told you, okay, this was my bad, that for this delete edge we would need to give a separate function, right? So this would be delete edge weighted. So see, like we learned from our mistakes, right? So now if we do this, see, from 3 here there was a connection to 4, and now there is no connection, so it's deleted. So I think that's it. We have covered adjacent matrix, and let me just put it here. Graph using AdjacencyList, and I'll give the source code in the description. So no worries, you will get it, and you will get it in a more structured way. So yeah, thanks for joining in the video, and I'll see you in the next one. Goodbye.